So the first speaker of the afternoon session is Cece Henderson, and she will talk about the Hypergraph Nash-Williams Conjecture. Welcome, Cece.
Thank you. Hi, everyone. It's so good to be here. I'm excited to talk to you today. I'm going to talk about some joint work with Michel Delcourt, Thomas Lesgourgues. If you are French, you are going to have a better pronunciation of Thomas's last name, and Luke Postle. We're going to start out with some background information. So questions in design theory are some of the oldest in combinatorics. For example, here's a question posed by Kirkman in the Ladies and Gentlemen's Diary in 1846. So Kirkman asked, how many triads can be made out of n symbols so that no pair of symbols shall be comprised more than once amongst them? Or in other less Victorian language, right? If we have a ground set of size n, can we find triples so that every pair of my ground set is contained in at least one triple? And in particular, Kirkman explored the case where each pair appears in exactly one triple. Now, there are a couple necessary divisibility conditions for Kirkman's question. Namely, your number of pairs needs to be divisible by 3, and also the number of pairs containing a single element also has to be even. If you work through that algebraically, you'll get that equivalently you need that n is 1 or 3 mod 6. So then, the question becomes, when is this necessary condition sufficient? Kirkman answered his own question, and in 1847 proved that it always is. So more specifically, it is possible to find a set of triples of a ground set of size n such that every pair of elements appears in exactly one triple if and only if n is 1 or 3 mod 6. And such a set of triples is called a Steiner triple system. A little bit of a misnomer here, right? Proved by Kirkman, called a Steiner triple system. Long story short, you should cite your own work when you are posing a more difficult problem so that someone more famous doesn't come along and say, wait a second, let me go prove an easier version of this and then gets all the credit. Okay, but if you've seen a Steiner triple system, the most famous example is the phonoplane. So you've probably seen this one. So this is a Steiner triple system on a ground set of size 7, which I've labeled alphabetically. Here's a set of triples, but most commonly this is visualized as this sort of triangle diagram, where each line, including a circle, represents a triple. So for example, we have this red triple ABC, and that corresponds to that red line there. And from this diagram, we can see that this really truly is a Steiner triple system, because every single pair of vertices appears on exactly one line. Okay, well, we're never done in math, right? So Kirkman proved his theorem, but there are a couple of natural ways to generalize Kirkman's question. He was talking about pairs of elements. He's talking about finding triples. These are some natural parameters to play with, right? So in particular, an NQR Steiner system is a set S of Q subsets of an N set X, such that every R subset of X is contained in exactly one element of S. Okay, lots of parameters floating around here. If you work through this, you'll see that a perfect matching is an N2-1 Steiner system, and a Steiner triple system is an N3-2 Steiner system. Okay, but if this is the first time you're seeing this definition, I think it can take a second to click what all these variables, how they correspond to our parameters. So instead, let's try and visualize what this definition is trying to say. So first of all, we're talking about a ground set of size n. We're graph theorists. I'm going to put n vertices. We're off to a strong start here. For the purposes of visualization, we're going to visualize what a Steiner triple system is. So we're talking about every R subset. In a Steiner triple system, R equals 2. So we're talking about a condition on every 2 subset. Well, I'm going to put in every edge. Now we have a complete graph. Again, we're getting into familiar territory here. And then we have this condition that we want to divide these 2 subsets into Q subsets, or in this case, 3 subsets. So then when I look at my complete graph, I'm trying to partition the edges into K3s, into triangles. So this motivates an equivalent perspective, F decompositions. In particular, given hypergraphs F and G, an F decomposition of G is a partition of the edges of G into edge disjoint copies of F. And a little bit of notation here, we'll use K sub n to the R to denote the complete R uniform hypergraph on n vertices. Okay, well then an NQR Steiner system is equivalent to a KQR decomposition of KNR. Back to our phonoplane example, right? We have our sets, we have the classic triangle diagram, but another way to visualize this is as a K3 decomposition of K7. And from this diagram, you can tell that this is really, truly, genuinely a Steiner triple system, because every single edge of K7 is contained in exactly one colorful triangle. Well, just as with Steiner triple systems, there are some necessary divisibility conditions for the existence of an F decomposition. The specifics vary problem to problem. We're just going to say that a hypergraph G is F divisible if it meets those conditions. Now, when do Steiner systems exist? The existence conjecture is a folklore conjecture from the mid-1800s that posits that the necessary conditions are always sufficient. So the existence conjecture posits that if n is sufficiently large and KNR is KQR divisible, then KNR admits a KQR decomposition. Or again, equivalently in our other perspective, the necessary conditions are sufficient for the existence of an NQR Steiner system. The existence conjecture was open, right, since the mid-1800s, and it was only fully resolved in the past decade or so, so quite recent. First, it was resolved by Keevash in 2014. He used a method called randomized algebraic constructions, and this really opened the floodgates, right? I do feel like once you know something is true, maybe it's easier to approach it with other proofs, right? So in 2016, Glock, Kühn, and Osthus published a different proof using a method called iterative absorption. And then even more recently in 2024, Delcourt and Postle used a method that they called refined absorption. I'm going to highlight that here because that's the method we use for the project I'll talk about later. And even more recently in 2024, Keevash provided an even shorter proof following in the refined absorption framework. Okay, this brings us to the Nash-Williams conjecture, a different Nash-Williams conjecture than was talked about earlier. With the resolution of the existence conjecture, again, we're not done. What about decompositions of non-complete graphs? Here, though, the question gets a little bit murkier because unfortunately, when G is not complete, divisibility is no longer enough. For example, a graph is K3 divisible if every vertex has even degree and the number of edges is divisible by 3. Well, then an example here is C6. We can check C6 is definitely K3 divisible, but it doesn't even contain a triangle. It definitely does not contain a triangle decomposition. Okay, so we need a more specific question. We need other conditions to ask a coherent question here. Intuitively, the higher the minimum degree of G, the closer the graph is to being complete, and hence addressed by the existence conjecture. So then a natural question becomes, is a high minimum degree in a divisible graph enough to guarantee the existence of a decomposition? The Nash-Williams conjecture of 1970 addresses the triangle subcase of this question. So more specifically, Nash-Williams posited that if G is a sufficiently large K3 divisible graph with minimum degree at least 3/4 times its number of vertices, then G admits a K3 decomposition. And in 1970, Graham provided a construction that showed that if this is true, then the constant 3/4 would indeed be tight. Before I talk about what's known about the Nash-Williams conjecture, I want to talk for a few minutes about why I think this is an important conjecture. So first, it's central to extremal combinatorics. There's a couple heavy-hitting theorems. I don't know what your first undergraduate class in combinatorics or graph theory looked like, but these showed up in mine, right? They're really classical results. First is Mantel's theorem from 1907. It gives a bound on the number of edges, such that if we're above that bound, then we're guaranteed a K3 subgraph and it's tight. And this is the base case for Turán's theorem, really at the heart of extremal graph theory. Next, we have the Karate-Heinel theorem from 1963 that says in a divisible graph, it gives a minimum degree condition for the existence of a K3 factor, where a K3 factor is a spanning set of vertex disjoint triangles. And this theorem is the base case for the Heinel-Semeretti theorem, another huge theorem in extremal combinatorics. So the Nash-Williams conjecture extends this deeply rooted lineage, right from the existence of a K3 subgraph to a K3 factor to a K3 decomposition. But wait, there's more. It's also relevant to a classical design theory question called the completion problem, right? Because if the conjecture is true, then any partial K3 decomposition of a divisible Kn, provided it has maximum degree at most 1/4 times n, is then completable to a full decomposition. And even more, the Nash-Williams conjecture generalizes another classical theorem, Dirac's theorem. So recall from 1952, Dirac's theorem states that if I have a large enough graph, it has a minimum degree at least 1/2 times its number of vertices, then that graph is Hamiltonian. Put another way, if my number of vertices is even, that implies that the graph has a perfect matching. Well, a perfect matching is an n2-1 Steiner system, so the Nash-Williams conjecture generalizes this to an n3-2 Steiner system. Okay, so if you take nothing else away from this talk, other than the fact that the Nash-Williams conjecture is important, I would be relatively happy with that. Okay, now we're ready to talk about what's known about the Nash-Williams conjecture. Unlike the existence conjecture, it is still open, but lots of progress has been made. We need to take a little bit of a detour here, though, because the best known progress was obtained by what we'll call tying the K3 decomposition threshold to the fractional K3 decomposition threshold. So that begs for a little bit of a vocabulary word here. A fractional F decomposition of G is a collection of F subgraphs of G, each with a weight between 0 and 1, such that the total weight on each edge of G over all the copies of F containing that edge is exactly 1. And as a little bit of a sanity check here, fractional decomposability is necessary for decomposability because a decomposition is a fractional decomposition where all of the weights are exactly 1. Well, with that, we can then define the fractional F decomposition threshold, which we'll denote as delta sub F raised to the star, as the infimum of all positive constants C, such that every graph G with minimum degree greater than C times its number of vertices has a fractional F decomposition. Okay, with that vocabulary out of the way, the best known result on the Nash-Williams conjecture is that minimum degree at least that rational times number of vertices guarantees the existence of a K3 decomposition in a K3 divisible graph, where that rational is about 0.83. Remember that we're aiming for 0.75. So this is not bad, right? We're getting there. Now, how was this result obtained? It's actually the combination of work from two different groups. So first, in 2016, Barber, Kühn, Low, and Osthus showed that for every positive epsilon, any sufficiently large K3 divisible graph G on n vertices with minimum degree at least that fractional threshold plus epsilon admits a K3 decomposition. So just to drive the point home here, showing that this fractional threshold is bounded above by 0.75, well, that would asymptotically prove the Nash-Williams conjecture. Then, in 2021, Delcourt and Postle improved the bound on that fractional threshold to the rational you see here. Okay, so that's the state of the art on the Nash-Williams conjecture. It's not totally done yet, but the ball is rolling, right? So now it's time to talk about generalizing the Nash-Williams conjecture, first to KQ decompositions. As a reminder, here's the Nash-Williams conjecture at the top here, and here's a folklore generalization to KQ decompositions. It posits that for every Q at least 4, if G is a sufficiently large KQ divisible graph with minimum degree at least 1 minus 1 over Q plus 1 times its number of vertices, then G admits a KQ decomposition. And just as with the Nash-Williams conjecture, a construction, this time from Gustafsson in 1991, shows that this minimum degree threshold would be tight if it were true. And just as a little bit of intuition for where this number is coming from, if we plugged in Q equals 3, we would recover that 3/4 number. So this sort of makes sense as a conjecture. Okay, what was known before we looked at this problem? Well, in 2016, Glock, Kühn, Low, Montgomery, and Osthus tied the KQ decomposition threshold to the fractional KQ decomposition threshold for all Q at least 3. So we're off to a good start. And then in 2019, Montgomery gave an upper bound on this fractional threshold. So it seems like we're sort of poised. We were looking at this problem. It seems like it's following a similar trajectory as the Nash-Williams conjecture, right? People have shown that it's actually equivalent to the fractional relaxation of the problem, and now we can start improving on this fractional bound. Unfortunately, though, we actually showed that the folklore generalization of the Nash-Williams conjecture is false. It's just not true. Even worse, even the fractional relaxation of the folklore generalization is false. So in particular, we showed that for every Q at least 4, that fractional threshold is strictly greater than the conjectured bound. Even worse, the folklore generalization is even off by a multiplicative factor. So in particular, for every positive epsilon and every large enough Q, at least 4, in terms of epsilon, that fractional threshold is strictly greater than 1 minus 1 over this rational minus epsilon times Q plus 1, where that rational is greater than 1. Okay, so not looking good for the folklore generalization here. I'll give a little bit of intuition about where our construction comes from. So first of all, by using independent blowups, it actually suffices to find just one counterexample, and then you can blow it up into infinitely many, infinitely large counterexamples. Recall that the join of graphs H1 through HK is the graph obtained by making each HI pairwise complete to one another. So then a counterexample for Q equals 7 is just the join of 5 C5s. It's a relatively simple graph. Why is that a counterexample? Well, it's a space barrier. There are simply too many cross edges between the copies of C5 to cover, given the number of internal edges, relatively sparse number of internal edges within the copies of C5. We were able to generalize this idea for all Q at least 4. Interestingly, though, we could not push it to Q equals 3. This construction does not disprove the Nash-Williams conjecture. And we were able to show that it's not just we didn't pick the right numbers or we didn't try hard enough. this construction simply will not work to disprove the Nash-Williams conjecture. So it begs the question, is the Nash-Williams conjecture also false and we just need a different counterexample? Or is there something special about triangles? Right? I don't know. It's hard to say. Okay, but I have a couple of minutes left, and that would be a pretty negative note to end on. So instead, let's turn to a more positive note and talk about generalizing the Nash-Williams conjecture, this time to hypergraphs. A little bit of vocabulary. An R-graph is an R-uniform hypergraph, and for an R-uniform hypergraph G, we'll use delta sub R minus 1 of G to denote the minimum number of edges containing any set of R minus 1 vertices in G. This is a really natural way to generalize what minimum degree means to hypergraphs. Okay, well then in 2021, Glock, Kühn, and Osthus proposed a hypergraph Nash-Williams conjecture. They posited that if G is a sufficiently large KQR divisible R graph with minimum R minus 1 degree at least, 1 minus something on the order of 1 over Q to the R minus 1 times its number of vertices, then G admits a KQR decomposition. What was known about this problem before we looked into it? Well, first of all, it follows from a 2014 construction of Kostachka, Mubai, and Verstraete that there exists infinitely many KQR-free R graphs G with minimum R minus 1 degree, at least 1 minus something on the order of log Q over Q to the R minus 1 times its number of vertices. So really what they're doing here is Turán theory. This makes sense. To have a decomposition, you have to at least have one copy of KQR. And then in 2023, Glock, Kühn, and Osthus showed that for all R strictly less than Q, all sufficiently large divisible R graphs with minimum R minus 1 degree at least, 1 minus something on the order of 1 over Q to the 2R times your number of vertices admits a KQR decomposition. So we were looking at this problem and we felt like there's quite a bit of space between the best known upper and lower bounds given here. So we felt like we had some room to play. And that brings us to our theorem. We showed that every sufficiently large KQR divisible R graph G with minimum R minus 1 degree, at least the maximum of the fractional threshold or the conjectured value times its number of vertices admits a KQR decomposition. And in 2025, Delcourt, Lesgourgues, and Postle improved the bound on this fractional threshold. So combining these two results, we get the following corollary. Every sufficiently large KQR divisible R graph G with minimum degree, at least 1 minus something on the order of 1 over Q to the R minus 1 plus epsilon times its number of vertices admits a KQR decomposition. So close to that conjectured value, right? We just have this little epsilon here. In my last 2 minutes, I want to give you a very, very general overview of the proof. And this is definitely aimed a little high at people who have maybe seen absorption before. So refined absorption is an absorption framework introduced by Delcourt and Postle in their 2024 proof of the existence conjecture. And a key definition here is omniabsorbers, a powerful absorption structure capable of transforming a partial decomposition into a full decomposition. So then the refined absorption framework has only 4 steps. First, you reserve a random subgraph x of G. Then you find this special subgraph called an omniabsorber, A for x, in the rest of the graph. Then you regularity boost what's remaining. And then you use nibble with reserves to find a partial decomposition of G without your special omniabsorber, covering all of the edges of the graph G without your reserves x. And then, by definition, your special omniabsorber is capable of decomposing anything that's left in X. Now, once again, they developed this for the proof of the existence conjecture, where we're working in a complete graph. So for us, we had to adapt this to our Nash-Williams setting, where our host graph is no longer complete. Again, in theory, when you look at this proof outline, this is not too bad, right? Instead of finding a random subgraph X of K and R, we're going to do it in G. Then we're going to find these special omni-absorbers in G, regularity boost G, use nibble with reserves in our graph G. Okay, in theory, not too bad. The real challenge was the second step here, finding this special subgraph of G. And here we were able to take the existence of KQR omni-absorbers in KNR as a black box. And then our challenge was to re-embed such an omni-absorber in our non-complete graph G. And to do so, we ended up developing a non-uniform Turán theory to accomplish this. Okay, that was a really, really high-level proof overview. Here's a bit of a summary of everything I talked about today. Thank you so much, and let me know if you have any questions.
Questions?
You think the Nash-Williams conjecture is true?
Ooh, that is hard to say. Very hard to say. I feel like I'm an optimist, and I feel like the 0.83 times the number of vertices, and we're going for 0.75. That right? Yeah, we're getting there, right? So I'm gonna say yes, but I don't know.
So I had a question. So
Yeah.
you're almost finishing your dissertation. So you did all this work before, ChatGPT became a thing. So, but in the last 2 months, it's really increased. Have you asked ChatGPT any of this stuff?
I haven't. I know Luke has been playing with it, so he might have a better answer. I feel like if ChatGPT is going to replace anyone, it's going to replace the people early in the careers, and so I'm not super interested in helping it replace me. I also feel like I'm at a point where it's still important for me to learn how to write these technical proofs.
Develop your voice.
Yeah, exactly. And so maybe once I'm more established, then I'll feel more comfortable asking it. But it's a good question.
I have found it not to be very useful in excluded minor stuff. And
Okay.
It's sort of related. So
Yeah. Maybe there's hope that we're still needed. Yeah.
How are we doing? Yeah, let's thank the speaker. The next talk is in 2 minutes. Did you know that Kirkman also was the first one to define